Hi, circuit students. Today we are beginning to talk about chapter 5, which discusses the idea of an operational amplifier. Now, an operational amplifier is sort of an interesting integrated circuit. And the approach that your textbook uses, which I think is quite wise actually, is to discuss it as a black box. So in other words, we're not really going to get inside and decide how an op amp works. We're just going to look at it as though we're going to look at it from the outside, how it connects into a circuit, and what it actually does within the circuit. So the first PowerPoint, there are 3 PowerPoints for chapter 5. Part 1 that we're covering today actually talks about sections 5.1 and 5.2 in your textbook. And we're really talking about the ideal operational amplifier. So the first thing is, what is an op amp? Well, an op amp is a component that basically boosts or increases a signal. So you can take a smaller input voltage and turn it into a larger input voltage. Um, or you can take an analog signal and boost it like with an actual, like a microphone to an actual amplifier. But the name operational amplifier actually comes from analog computing back in the 1960s, where the operation stands for mathematical operations. In other words, add, subtract, multiply, divide, and so forth. But basically, in analog computers, these circuits were used to do mathematical operations. And so they became known as operational amplifiers, or op amps for short. And the name is stuck. Although right now using them more or less as a signal booster, sometimes as a voltage regulator, is a more common practice. But what they look like is just a little chip. They just look like a little, any sort of a microchip, a solid state little chunk with legs on it that you can plug into a breadboard, which is, of course, in lab what we will be doing. But so the objectives of this first part of chapter 5 are to be able to identify and name the terminals of an op amp, then to be able to state the constraints that characterize an ideal op amp, which means we're also going to have to define what an ideal op amp is, because the ones that work in real life, of course, are not actually ideal. And then the third thing is to know how to recognize and analyze the following op amp circuits: inverting amplifier, summing amplifier, non-inverting amplifier, and a difference amplifier. All right, so to begin accomplishing that, we're going to take a look at this picture. So op amps in electric circuits are drawn as a little triangle. There are 2 terminals, a positive terminal and a negative terminal for amperage, and there is a positive terminal for voltage and a negative terminal for voltage. Now, here we have a voltage supply, which is called VCC, which feeds into the positive power supply, or that is the power positive supply, I should say. And then we have the same VCC here that feeds into the negative power supply. We have 2 inputs for amperage, one of which is non-inverting and one of which is inverting. So they're given the signs positive and negative, but the inverting terminal is assigned negative. And what that means is that if we put a feedback loop here, which we'll learn about a little bit later, it will change the sign of the wave. Or another way to think about it is it will offset the wave by 180 degrees. If you put the feedback on the non-inverting terminal, it will not invert the wave. It'll come out the same, in the same phase as it went in. All right, so we've identified the non-inverting input, which is referred to as IP, the inverting input, which is referred to as IN. You can also think about this as being I positive and I negative, okay? Then we have the positive power supply, which is assigned the variable V positive. and the negative power supply, which is V negative, V with a negative sign. Then we have I sub C negative, which goes with VCC, or the battery or whatever is connected to a common terminal with the positive VCC. So these are, if you look at a chip, I think this is kind of weird because you learn looking at a triangle and then you have to convert it to the pins on a chip. But each one of the pins on a chip, there's usually 10 pins on a microchip. And you can see that 1, 2, 3, 4, 5, 6 or 7 of them are used in the chip that is an op amp. A couple of the pins then are going to just be blanks. They don't really do anything. All right, so what happens with an op amp? Well, if we look at the voltage, now look at this scale, we go from VCC to negative VCC. And what this is saying is that the signal on VCC, the voltage on VCC, the positive and the negative, is going to be amplified by some gain factor A, okay? And that value is going to be the maximum that we can get out of here while we are in the linear range. Now, is an op amp linear? Well, not inherently. An ideal amp always operates in this linear region between the maximum negative voltage and the maximum positive voltage, which are referred to as saturation. So what does that mean? That means that the voltage V sub O is going to be between VCC negative and VCC positive, or else it is not a linear device. The other thing is when we hit positive saturation or negative saturation, the curve really, this is excruciatingly idealized. So it's not exactly going to look like that, but suffice to say that for now, the op amp can only be ideal in the linear region of operation. So when we hit saturation, it's no longer got a chance to be ideal, and we can't analyze it using ideal methods. So then the question, op amps are inherently linear devices, true or false? False, because they are only linear when they are ideal and when we are between saturation voltages. All right, so so this just talks about how we're going to limit this. So the first thing is when we have an operational amplifier and we understand that we can only do our analysis when it's in the linear region, we have to make sure that we're in the linear region. And yet mathematically, we really can't tell if we're in the linear region except by checking our values of V sub O or V sub S. And the first thing is though, so what we do is when we start our analysis, we assume that we're in the ideal, that the op amp is in an area of is linear, but is also an ideal operation. And the first thing that requires is that we have feedback. All right. So negative feedback just means that we put a resistor on the negative terminal. We can also do a positive feedback on the positive terminal. But hang on a second. You see what they've done here? This is positive, positive, negative, negative. Okay, so here's my inverting. Okay, when you come up here to the next picture, they have negative positive. So there's a little bit of a discrepancy with the picture. Okay, but it doesn't really matter. We have negative feedback if there is the resistor going on the terminal between the output and the negative I sub n. Okay, if the feedback is over here, in other words, if the resistor is on this terminal, the positive, then it's a positive feedback. But in any case, that's the only chance we have of it being in the ideal range. So we have to check to make sure there's negative feedback or positive feedback. And if there's no feedback, then you have no chance of it being an ideal op amp. All right, so first of all, so here's the other thing. what has to be met? Well, the condition has to be that the output voltage has to be between the negative input voltage and the positive input voltage. So the way they phrase it here, how can we be sure that the op amp is operating in the linear region? We can't. We must assume that it's operating in the linear region and then complete our circuit analysis and then check our assumption, which is easier than it sounds. We can just set up a little table and make sure, just check what that V sub C is, negative and positive, and make sure that our value of V sub O falls between them. And then just to do that visual inspection to make sure that we actually have a feedback loop. All right, so here we go. This is just a diagram of a chip, a Texas Instrument microamp 741 op amp. And basically what it shows you is what the pins are. We have offset N1, we have some NCs, we have V sub C, VCC positive, VCC negative output, and then we have some no connections. But each one of the pins has a different function or no function at all. There are other types of op amps, and I actually purchased the op amps that are called for in our lab to make sure that we didn't have an extra confounding factor. So the ones that I have purchased that we'll use in lab beginning on Wednesday actually do meet. We can find a spec sheet on that op amp, and then we should be able to know what we've got for those characteristics. Okay, here's just a little bit more about the TI Micro A741 op amp, but the spec sheet, as you can see, everything is laid out. All right, so the next slide, in Micro Amp 741 op amp, the voltage gain in the linear operating region is 200,000 volts per volts. That's that gain factor, that A that we talked about. Since both of the axes have units of volts, A is actually, the gain factor is actually dimensionless. But in an ideal op amp, the voltage gain in a linear region is infinity. That is the definition of the voltage gain in the linear region. Now, I wanted to take a minute and show you on our Moodle page, I put up a couple of basic assumptions for operational amplifiers when we are dealing with in the ideal range. So we're talking about what gets us put there. So we always begin with these assumptions. First, we check for the feedback loop. Then we check, and V negative and V positive should have the same voltage, although it does not hinder our analysis if they don't. We can still do an analysis with a different value on V negative and V positive. Also, there is no input current. Well, is that ever true? I mean, what does that mean? It means that the resistance is infinite, right? But it's not ever true, but it's something that we can approach, and we can use it when we are analyzing ideal operational amplifiers. Okay, so in that range, the input resistance is infinite. Well, I guess I have that. I didn't pull that one up yet. So let's go back here to my screen. Right. So like we said, the voltage gain is infinite. And what does that also mean for us? The input resistance is also infinite. There's no amperage. So here we go. In ideal amp, the output resistance is 0. So our input resistance are infinite. Our output resistance is 0. Our input amperage is 0. And our gain factor is infinite. All right. So here's another question. In an ideal op amp, the voltage gain in the linear region is infinite. Therefore, what is VP minus VN? Well, that's the positive minus the negative, right? So what does that mean? If this was 5 and this was negative 5, that would be 5 minus 5. So we're kind of doing this weird thing with signs, and that's equal to 0. All right, so another question. In an ideal op amp, the input resistance right here is infinite. Therefore, the current flowing into the input of the op amp, both IP and IN, are 0. That is an assumption of an ideal op amp. All right, so we're going to get into some analysis in just a couple of minutes here. We still have to kind of think about some of these other ideas. And what we're basically talking about is what classifies us as an ideal op amp rather than a real op amp, which we'll deal with a little bit later in the chapter. All right, so we usually assume the op amp is ideal. We have to make that assumption. And the only thing we really need to check before we make that assumption is whether we have a feedback. And then the next we'll have to operate, if it's we have to see if it's operating in a linear region, which we don't really look for linearity. What we look at is that it's between V sub C positive and V sub C negative. And then we assume that linear relationship. All right, so this allows us to make these two important assumptions, that VP is equal to VN, right? And that the current entering both of the input terminals is equal to 0. Okay, so on this slide, we start to look about analysis. How do we actually analyze an ideal op amp? Well, the first thing is we check for that feedback path. If it exists, then we assume the op amp operates in the ideal region. That doesn't mean it does, it just means we're making that assumption, making our calculations, and then afterward we'll check. After we check for that feedback, we write Kirchhoff's current law equation at the inverting input terminal, and then we solve it. And then we use that to compare or do that check of the op amp's output voltage to make sure that it's between VCC and negative VCC. All right, so here's a little solution. It asks us to find a V sub 0. That is the output amperage for source voltage is V sub S of these different values. So in other words, we start with a positive 0.4 V sub S, then we move to a 2.0 VCS and so forth, and we check these 6 different values. So what we first have to do is to check for negative feedback loop. There it is. We've got that resistor on the inverting terminal, so we're okay. Then we write the Kirchhoff current law after we determine, remember, we have VP equals VN, IP IN equals 0, so we have 0 minus V sub S, 0 minus V sub O over those resistances. So remember, V, just easy, is equal to IR. So I is equal to V over R, and when we add them together, those have to equal 0. Then we can solve for V sub S and V sub O with a little bit more manipulation. And then we're going to we find out what this amplifying factor is, this A, after we solve it. Okay, and then we set up a chart. Okay, so for different values of V sub S, V on the voltage of the supply, we calculate V sub O by multiplying it by the factor of a -5. And then we check that value to see if it's okay. What does that mean? Okay means it's between the negative and the positive. Okay, here, the negative is 15. So this and this are okay, but this is too big, isn't it? This has too big of an absolute value. The 3.5 V sub S yields a -17.5 V sub O, and that is not in the linear region because the negative terminal saturated at -15 volts. The positive terminal saturated at 10 volts. So we have to check these numbers. And once again, we see that the -2.4 V sub S yields a number that's too high. And so that is not ideal. So we have 4 values that we could evaluate as assuming ideal and 2 that we cannot. All right, so now that we've got that information, we find the range of input voltages V sub S for which the op amp operates in the linear region. Okay, well, we can go back here and take a look, and we can see our V sub S. Here we saturate at 2. V sub S at 2 saturates at -10. And Then on the other side, we're going to saturate at -15. So we have to check those two values right here. I don't really like the way that was written, but it's still okay. Never mind. So then we do a V sub S, what we calculate V sub S from the 10 and the -15, -5 and -5 are our amplifying factor or our gain. And we find that -2 volts right here, that's the smallest value, up to 3 volts is going to be where we are operating or where we may be operating in the linear region of that curve, or I guess I could say for an ideal op amp, these are the ranges of values that would produce the linear portion of the curve, that would fall into the linear portion of the curve. All right, so at that point, then we can take a look at the inverting amplifier and we find that value. And then we know that this design equation, which is the amplification factor, that only works if and only if V sub O is between these two values. Okay, so we're pulling up that information about Kirchhoff's current law and our knowledge of series and parallel resistors, well, just series resistors really, and then developing these equations. And we find, if you look at this, V sub O is equal to minus R sub F over I. V sub O is equal to minus R sub F over I. So it looks like the gain is the same as those two in this particular configuration, which is a very common configuration. All right, so on this slide, in describing op-amp circuits, the term inverting just means changing the sign. That's all it means. So you're off. You could also say it's off by 180 degrees, shifts it out of phase, but inverting means changing the sign. All right, the last slide talks about designing an inverting amplifier with a gain of 10. Okay, so we know here that the gain is 10. V sub O is going to be equal to minus 10 times V sub S minus 10 times V sub S. So we get our values, use plus or minus 12. So we know what our values are. And then choose a feedback resistor and input resistor such that the ratio is 10, one possibility is shown below. Okay, so once again, we just design for a particular range of voltages on the supply that will produce the desired design of that op amp. All right, so in my opinion, the math of ideal op amps is pretty straightforward. It's a little weird to think about because first we're only talking about an ideal component that doesn't really exist, and then second, we approximate it in actual operation. And then the second part is that we're not really talking about how that happens. How does the voltage get magnified or amplified? We just say, well, it's just this little special thing, little black box, and everything is fine. So we just make that assumption. All right, so thank you very much for your attention. Let me know if you have any questions. I've posted the homework problems, and we'll look forward to talking about this more next time.